Anyway, so last time we looked at equivalence relations on a set. And we usually denote equivalence relations by the symbol. And we saw that the main interesting part of equivalence relation is that it gives a partition of the set. So, gives a partition of A, and by A quotient we denote the set of all distinct equivalence classes. So more or less, in a way, mathematics done is to break any mathematical structure into equivalence classes and study each one of these classes with respect to some property. Certain characterizing property will be common to all the members in a particular equivalence class. So that's one aspect which we'll be using many times, equivalence relation. The other one that we'll be using would be the partial order. This is what I will discuss today and see how far I can push it today. So if P is any non-empty set, and a relation R, this notion of equivalence is modeled with the properties of equal, with numbers. The notion of partial order is modeled, then I would say really modeled with the relation less than or equal to. Relation R on P is said to be a partial order The equivalence relation and partial order share two properties in common, but one property mentions it as opposite. One, if one R is reflexive, which was also the case with equivalence relation, that is P R P, for every P is P, and two, R is anti-symmetric. That is, in the equivalence relation, P R Q implied Q R P. But now, that both can happen only when P equal. That is, P R Q and Q R P implies P. Only time, it doesn't mean that whenever P equal to Q, you will get PRP. It says, if at all it happens, it can happen only in the case of P equal to Q. It doesn't mean that it happens in P equal. Okay, remember that. And 3, R is transitive. That is, P R Q and Q R S implies PR. Then it's called a partial order relation on P. If these three properties are satisfied. We'll give a number of examples, a few examples right now. Before that, I'll make a few remarks. Now, it will be a good exercise in understanding the meaning of each one of this, is to give a relation R which is reflexive but not these two, a relation R which is these two but not this, these two but not this, these two but not this, and then all these. and I'm not requesting you to construct that just to say that these three are independent statements. One does not imply the other. Okay, let me straight away give you some examples of maybe some terminologies called for these or these. Okay, if just like we use this symbol for equivalence relation, we denote a partial order relation by the symbol, somewhat distorted symbol of is less than or equal. Just to remind us that it is modeled on that. And then we say P together with the partial order is a partially ordered set, or just short form partial. Okay, these are some terms which I'll be using. So from now on, we are going to look at a partially ordered set. Now, certain things to be remembered, we'll see examples of this. In a partially ordered set, it is not necessary, maybe I will even, if A is related to B, we say A precedes B. But if you will see the text notation for this symbol, it's only precedes. Later notation. A precedes B or B succeeds. I never understand the spelling of this, how many C's and how many succeeds A, or A is a predecessor to B. This I never tried to spell. Predecessor to B, or B is a successor to A. That's why mathematics is simply with a symbol of vertical. Okay, the second comment is in a person, if A and B are such that either A precedes B or B precedes A, then both cannot happen, because both happen then A equal to B. Then we say, only case where it can happen is A. We say A and B are comparable or comparable. It is not necessary that every pair is comparable. Now we'll see all these exhibitors in some simple examples. Example 1. This is modeled on less than or equal to, so on number, so the less than or equal to a number, any set of numbers. Take the natural number is less than or equal to, or you take all the integers is less than or equal to, or take the rational numbers is less than or equal to, or the real numbers is less than or equal to. These are all. But these are process. In each one of them, every pair is comparable. There is a law of trichotomy of real numbers. Given any two, law of trichotomy of real or integers or anything, that given any two numbers, either A is less than or equal to B or B is less than or equal to B. So in these posets, all, every pair is a pair. Okay. And of course, I will just write example 2 as lexicographic ordering. Ordering is a partial order. Just like how the words are arranged in a dictionary. You first compare, you take a partial order, take a Cartesian product of that, and then you compare an ordered n-tuple by first comparing the first two elements, and then if they match, compare the second, and so on and so forth. So I will come to that whenever it is necessary. I will just put it as lexicography. I will proceed with the other examples that I want at the moment. Here is an example, which is a very important example, number 2. So let's take the natural numbers, and let us take this relation. What is that relation? A is said to be related to B if A divides B. That means A is a factor of B, or B is a multiple of A. Whenever I say B is a multiple of A, I mean integral multiple of. Now this is a partial order because A divides A, reflexive. A divides B and B divides A, then A must be equal to B. If A divides B, B divides C, A divides C. So automatically this is a partial order. Note that in this poset there are pairs that are not compared. For example, if we take 3 and 17, neither 3 divides 17 nor 17 divides 3. So neither A is 3 is related to 17 nor 17 is related to. This is a random example that I can now give any number for. 3 does not relate to 17 does not relate to 3, so they are not compared. So that's what I said in a partial ordered set. Not every pair will be compared. That is why it's called partially ordered. Some pairs are comparable, some pairs are not. They are not fully related. I'm going to write only those examples which I may use immediately. Example 3. Let us take any set X, take any set, and then let P be the power set. The set of all subsets of X. Then clearly, if we take the relation to be subset or equal, A is related to B if A is subset or equal to, so is a positive. Because A is the subset of itself. If A is a subset of B and B is a subset of A equal to B. And if A is a subset of B and B is a subset of C, A is a subset. So these three properties are easily verified. Here again, you will see that given two subsets, it's not necessary that either this is contained in the other or vice versa. There may be some common portion and some non-common. So here again, not every pair in P is compared. So in general, this is what will happen in a particular array. Not necessarily all pairs are compared. All these examples I will keep on using. So let me take A and B be any two sets. non-empty. And then let me use this notation f sub AB to be all functions whose domain is a part of A and codomain is B. So let me write it as the set of all functions which map the domain F, which is a subset of A into. So the function need not be defined on all of A, but a part of. So its domain is a part of A and codomain is B. So take the collection of all such functions, then the natural partial order you will have is, remember on the first day we talked about extensions, okay, or restrictions. So for F, B belongs to FAB, we define F is related to G if G is an extension of what is meant by extension? The domain of G must be bigger than the domain of F, at least as big as the domain of F, and in the common portion they agree. So that is the domain of F is a subset of domain of G, and Fx equals Gx for every x. The common portion to function x. Then we say it's an x. So it's easy to verify that all those three properties are satisfied. F is an extension of itself, so Gf equals Gg, and the remaining things are. One more probably example. First, give a very simple example. So let's consider V to be R3 vector space, three-dimensional vector space over R. Whenever I write R3, the vector space over the field R. Then let V be the collection of all linearly independent sets. Then same theoretic argument. So this is a simple example. Again, in this there are two linearly independent sets need not be comparable. So one linearly independent set need not be a part of another linearly independent. Again, this is an example where pairs need not be comparable. Now, this a more generalized version of this is what I will take. Let V be any vector space over a field F. Any vector space over a field F. Then, now I have to be careful about linearly independent set F. A finite set of vectors u1, u2, uk in V is said to be linearly independent. This is the usual definition. If alpha 1 u1 plus alpha k uk equal to the 0 vector, but only if alpha 1, alpha 2, alpha k are where alphas are in the interior. Alpha k. Now, about the only linear combination of these vectors that gives the 0 vector is the 0 linear combination, trivial linear combination. Now, we will also define what is meant by infinite set being linearly independent. An infinite set is said to be linearly independent if every finite subset is linearly independent. An infinite set B in V is said to be linearly independent if every finite subset of B of course, there is a convention we have to treat the empty set as a linearly independent set. Okay, now this would be, now take B to be the set of all linearly independent sets in the vector space and put that set. With this definition of linearly independent set, then B is B is the set of all linearly independent sets. Take the set of all linearly independent sets. B, that collection to the subset relation is okay, again, there are pairs which are not comparable. Okay, so let me hold the example for the stage and one can go on and on with any number of examples for this process. So at least there are processes in which every pair is comparable. There are processes with pairs which are not comparable. So if you take, let me, where was the first example? Well, all of them are of course. This is the first time. One is example 1 is where was what was 1? Remember n less than or equal to q less than or equal to z less than or equal to or these are all now look at the first example set of examples. These are examples in which you can think of this as a part of this or a part of that or a part of this, right? N is a subset of Z, N is a subset of Q, N is a subset of R. So what this says is if you take a big partially ordered set, take a subset in it and restrict that order only to those elements in that subset, that becomes also a partially ordered set, and we call that a subset. So that's the first remark. I will erase these examples. I hope when I can refer to them whenever I want. So some remarks or whatever you call them. Observations. Remark 1. If P is a poset and S is any subset, any non-empty subset, subset of P, then S, the same relation, is a poset, is also a poset. We call this subset. The substructures are the ones which always in the study of algebra. We have a group, we talk about subgroup. What is a subgroup? It's a subset, same operation restricted. You have vector space, you have a subspace. What is subspace? A subset with the same operation restricted, and you get the same part. So exactly similar thing, ring, subring, module, submodule. The sub-business will be there everywhere, all over the place. Now look at these examples, the first set of examples where I have these natural numbers less than or equal to, etc., etc. These were processes in which every pair of elements was comparable. So now there is no partiality there, no partial business. It is totally ordered. Every pair is so a partially ordered set is such that every pair is comparable. We no longer call it a partially ordered set, we call it a totally ordered set. So that is remark 2. If a poset every pair is comparable, then we call it a poset, totally ordered. See, there are many such terminologies that are there: partially ordered set, totally ordered set, well ordered set. These are all meaning different things. Be careful. A poset is a poset in which every pair is comparable. Okay, the examples are, these are all, every one of them is a totally ordered set. Real numbers are totally ordered, but not well ordered. There is something. What is well ordering, that will come later. These are all very ticklish problems like set theory, with well ordering maximum choice, 50 lemma. There are many things, outdoor maximum choice, Zorn's lemma, which we will see. We will see Zorn's lemma, which seems to be a more understandable version of all those other things. All are equal. However, if you take a poset which is not a poset, or even if it is a poset, there may be some sub-posets which are totally ordered. The smaller fellows may be totally ordered. Even if not a poset, there may be sub-posets which are totally ordered. For example, let's consider this poset. This is not totally ordered. Of course, if you take already a totally ordered set, then every sub-poset is also totally ordered. That's not a big deal. So now what I am looking at is, even though the original poset may not be totally ordered, there may be sub-posets which may be totally ordered. Take, for instance, take all the powers of 2. 1, 2, 2 squared, 2 cubed, 2 to the power of 4, etc. It's a subset of n. So S is a sub-poset. Now you see, if you give any two elements, one is of the form 2 to the power of m, the other one is of the form 2 to the power of n, then one of them will have to divide the other, because if m is greater than n, 2 to the n divides 2 to the m. If m is greater than n, 2 to the n divides 2 to the m. If m is equal to n, then it divides itself. So therefore, this is a totally ordered set. This is a totally ordered set. So subset. totally ordered. So even though the original partially ordered set may not be totally ordered, there may be sub-process which may be totally. Such things are called chain. A subset which is totally ordered is called a chain in that. In a totally ordered poset, everybody is a chain. But in a general poset, there may be chains, there may not be chains. A sub-poset may be chain, may not be chain. So, this is the terminology. So, these are all the language that is necessary to eventually get to the very famous theorem called the Zorn theorem. All these are only machinery and or language. So, totally ordered subcode or called a chain. There is a link. That should not be confused with the logic. It's called a chain. For example, in this, I could have taken any fixed number k and looked at all the powers of k. 1, k, k squared, k cubed, k to the power of 4. That will be a chain. The typical chain in this process. Let me think and can do what I want to as fast as possible. One of the main ideas is to look for what is known as maximal element. So I'll carefully define that term maximal element. By the way, if this is a poset, this is also a poset. What is this? This is a reverse relation. If A is related to B in that relation, we say B is related to A. So that is a poset, this is a poset. So if I study about maximality, I am also studying about minimality. So I will really be worried about this maximality. So, this has to be very carefully understood. Maximal is different from maximum. Okay, so it should not be confused with the word maximum. So let me make the statement. So let be a poset, and then I'll give you some examples. Consider a poset. Then an element M in P is said to be a maximal element. I am not using the word the maximal. A maximal element if follows. P belongs to P and M is precedes P implies M equal. It's a negative definition. Nobody can beat it. It doesn't mean that he beats everything. Nobody can beat him. The only fellow who can beat him is himself. But not to finish himself off. So this means M, that is M, there is M does not precede any element other not equal to any other element. M does not precede any other element. Or M does not have a successor. M does not. Then it's called a maximal. Maximum means he succeeds everybody else. So let me make that. This should not be confused with maximum. M is called M naught. M naught in P is called, I will say the question, there's only one maximum. I will come to these things later. The maximum in P, if P for every P in it beats everything. It really beats everything. P is less than a protein, less jam or equal to the word. What is it here? The minimal is exactly the opposite. Here succeeds replaced by precedes, precedes replaced by succeeds. So let's look at some examples. Okay, let's some remark. It's a similarly minimal. Similarly minimal and minimum. You have to justify that third. One. A faucet may have one finitely many or infinitely many maximal. Infinitely many, they may not have any maximal element. It may have some 10 maximal elements, finitely many, or it may have even an infinite number of maximal elements. So that's why I said A maximal may not be there. Similarly for minimal. But if a faucet may have no, I should write no, one, finitely many, but if a faucet may have no maximum, but if it has a maximum, it has to be only one. Justify that. That is true. I leave it as a question. How do you justify that? Let's look at some examples. First thing is to understand by example. So example 1, let us take real numbers with less than 5. Does it have a maximal element? That is, who is a maximal element? Who does not have anybody who beats him. But if you give me any real number, I can always beat him by adding 1 to it. So no maximal element. No minimal element. Let us take this example. That is the set of all positive integers where the relationship is A related to B if A divides B or B is a multiple of. Now let's see what should be a max. Suppose M call some A, N in N is a maximal element. Suppose N in N is a maximal element. What does that say? P less than or equal to M or M less than or equal to N less than or equal to P must imply N equal to P. Somebody beats him, he must be equal to P. Is that true? For every N, somebody beats him. Who? 2N, 3N, 4N, 5N, all beat them. So for every N, we have N divided 2N. Therefore, no N can be a maximal element. So there is no maximal element in this text. What about the minimal element? Let me give you the same set. Let me give you example 2 where P is the set of all prime numbers. Who is the set of all prime numbers? Now what about maximal element? If this fellow divides P, a prime number will always divide twice that, thrice that, and so on and so forth. So again, no maximum. What about minimal element? All of them are minimal. If somebody divides a prime number, is that correct? I have not. There are always this confusion with something whether one should be a prime or not. One is not written as a prime. So the only fellow who can divide the prime number is himself. Other than one is not included here. So everybody is a minimal element. Everybody. So how many minimal elements are there? This is a very strange case. Everybody is a minimal element, no maximal element. So all kinds of crazy things can happen. Okay, that's what I want to say. Let us. I will skip some examples. I'll come back to those examples because I want to get all the material for the Zorn Lemma ready. Okay, so that I can discuss Zorn Lemma on after this. Okay. Yeah. Everybody is a maximal element. True or false? So what is the situation with the prime fellows then? The strangest thing happened. What can you say about this prime poset? Sometimes I put question mark. What can you say about this prime poset? Who are minimal elements? Who are maximal elements? They all speak. It's like a parliament in India. and nobody walk out. So in the case of prime poset, who are the maximal, who are the minimal? Okay. So let me put it the question mark, please. Please, which elements are maximal, which are minimal? Think about it here. Yeah. Right. I know you have a good observation, but you have no answer that question. Okay. I'll leave it as easy. I want to quickly get so these examples you can easily get some carefully. Some of the things I will be sloppy in a hurry. Okay, so now the question I want to ask is, most of the time in a partially ordered set, we are looking for a maximal element. When we are looking for, one more example I can give, but I want to, let me come to that example. Most of the time in a partial order, we are looking for a maximal element. But that maximal element may or may not be there. For example, when we are looking for a basis for a vector space, what we are looking for is a maximal element in the poset of the set of all linearly independent sets. Okay. And similarly in extension theory, we are looking for a maximal extension. So there are always problems in which we are looking for a maximal element in a poset. But we are not sure whether a partially ordered set will have a maximal element or not. So we want to now look at a set of conditions under which we are guaranteed the existence of a maximal element in a partially ordered set. So I will put all the details about these examples in this thing. More examples I will put in. By the way, most of the, from now on in the lecture notes, there will be a little bit more than what I do in the class. There will be more examples, some remarks will be extra, I expect. So therefore, I expect that we go through the notes a little bit more seriously. Okay, so the question is, under what conditions, at least, can we assert that a poset be as a maximal? This fundamental result is known as the Zorn. Wherever you are looking for maximal element in analysis, you will always do Zorn. That's the fundamental result. If that condition is not there, we don't know how to prove. This is only sufficient condition, but we don't know otherwise. Other way of proving the existence of a maximum. Okay. So now I am going to. This is given by Zorn. I don't know why it is called Lemma. Some must say something called two-piece Lemma. Another one is called Hausdorff maximum principle. The one is called axiom of choice. All of them are equivalent. So one is called axiom, one is called principle, one is called lemma. Okay. So I want to get to the Zorn's lemma and then give you two applications of this. General, okay, so the general vector spaces and so on and so on. One application very easy to see, but the other one will have to wait for to understand the full power of it. So the Zorn's lemma says, under what conditions will a poset have a maximal element? This condition has got to do with how the chains in that poset are structured. That's why I introduced the terminology chain. What is a chain? a chain is a subset in which every pair is comparable. Now, therefore, I am going to go, one more ingredient is what I want. Okay. This is what is known as upper bound for a subset. Now, this is a very obvious definition. Okay. So, suppose S is a subset of P, watch the word, then an element U in P, that U may be in S or may not be in S. As long as it is in the process, that's okay for me. Okay. U in P is said to be an upper bound for S if it dominates everybody in S, or it succeeds everybody in S, or everybody in S precedes you. Everybody in S is comparable to you, and in that comparison, S comes below. Every S comes below. Then U is called an upper bound. I will make a remark, take the theorem. A subset may or may not have an upper bound. May or may not have an upper bound. Unbounded. For example, if you take R greater than or equal to, and you take all numbers between 0 and infinity as your S, there is no upper bound. In R, there is no real number which dominates. So all numbers greater than or equal to 0. Has no upper bound. So a set may or may not have an upper bound. Now, the Zorn's lemma is a theorem or a result or an axiom which says that if in a poset certain special types of subsets have an upper bound, if in a poset certain special types of posets have an upper bound, then that poset will have a maximum. Which are the special types of subsets? Chain. The special types of subsets are chain. So, Zorn's lemma says that if in a poset every chain has an upper bound, then the poset will have a maximum. So, let me start the statement. This is a very fundamental. Every chain has an upper bound, then there exists a maximum element if every chain has an upper bound, then there exists a maximum. Take for instance the natural numbers with divisibility. Then you had a chain 1, 2, 2 square, 2 cube, 2 to the power of 4, etc. That does not have an upper bound. That's a chain, but it does not have an upper bound. So Zorn's lemma doesn't give any result about that concept. However, let us now look at this very quickly. I will go through that in the next class again. Let us take a vector space V over there. Take a vector space V over, and my B is, the poset is the collection of all linearly independent sets with the subset relationship. And recall the definition of linear independence. The finite set is said to be linearly independent if the only linear combination that gives zero vector is trivial linear combination. And an infinite set is said to be linearly independent if every finite subset is also linearly independent. If every finite subset is linearly independent. Now this is my poset. Consider a chain. What is a chain? Is a subset of the poset. That is, the elements of the chain are elements of the V. The elements of V are linearly independent sets. So the elements of C are linearly independent sets in the vector space V. It is a chain means if you take any two linearly independent which are members of C, one of them will be contained in the other. They are comparable. So consider a chain. Okay. Now, does it have an upper bound? Consider any chain. If the answer to this question is yes, Zorn's lemma will tell us, in this poset every chain has an upper bound, there must be a maximal element. What are these elements? Linearly independent sets. So there will be a maximal linearly independent set. A maximal linearly independent set is called a base. So every vector space will then have a base. So I have to show that if you take any chain, it has an upper bound. What is your guess for the upper bound? Some set which must be bigger than all of them. The easiest way to get a set which is bigger than all of them is take the union. But when I take the union, I must make sure it is also in the poset. That means that the union is also linearly independent. Prove that. Okay. Then define K to be equal to union of all the K belonging to C. Oh, there is K. Say B belongs to C. Every linearly independent set which is an element in C, take the union. Now claim K is linearly independent. Claim K is linearly independent. 1, 2, therefore K belongs to B, and clearly C is contained as equal to K for every B is contained as equal to K for every B. So therefore it's an upper bound. Therefore K is an upper bound. Okay, so therefore there will be a maximal linearly independent. This is how the existence of a basis is proved. This is a kind of cheating. This is exactly what axiom of choice. I will state axiom of choice in the next class. Now the only trick here is to make sure that this is linearly independent. How do I show that it is linearly independent? If it is finite, then I have to verify the standard. How do I show that? Suppose K is finite. It will have how many elements? Finite number of elements. Say K1, K2, Kn. Because it is the union of all these B's, K1 must belong to some B1, K2 must belong to B2, Kn must belong to Bn. But because it is a chain, among the B1, B2, Bn, there must be a biggest fellow. So all the K1, K2, Kn will belong to that biggest fellow. That biggest fellow is linearly independent. So therefore this set will be linearly independent. But suppose K is infinite. What should you show? Every finite subset is linearly independent. Take any finite subset back to the old argument. So that's the way it is shown. I will leave the details to the module. So therefore, this is the way one asserts that any vector space or any field will have a maximal linearly independent set, and a basis is defined to be a maximal linearly independent. Similarly, you show that in any inner product set, say there will be a maximal orthonormal set. Same type of argument. Instead of B to be set of all linearly independent sets, take B to be the set of all orthonormal sets. Put the same argument, use Zorn's lemma, and get maximal orthonormal. That is called an orthonormal base. Similarly, extension, maximal extension. So all these maximal theorems will use this Zorn's lemma. So what I want to do next time is give these examples probably in a little bit more detail, where the Zorn's lemma is used, and then in a little tricky situation, I will try to tell you various versions of this Zorn's lemma. They totally look totally different, but they are all equivalent. If you have one, you will have all the others. They are all equivalent states. After, I am not going to prove all of them. So I think only one suffice. I have spent time. In fact, once I gave only special 7 lectures to prove the equivalence of all these statements of equivalent statements of Zorn's lemma. I am not going to do it because time is short. It was more relaxed in those days. So what I will do is, I will first, in the next class, I will link all these things to Zorn's lemma, maximal element things, and then give you the various equivalent versions, at least some hint of it, and at that time we will see another landmark axiom in the set theory, namely the axiom of choice. The axiom of choice and its equivalent Zorn's lemma and the continuum hypothesis are two important axioms what we will be repeatedly using, and neither of them can be proved to the other. Right there. Last time I did not send the notes because there was only one lecture. So what I will do is I will complete Thursday and then 3 lectures together. I think probably after the Thursday's lecture, the video can be uploaded after the